You are sitting in a room that feels stable. The air around you behaves the way you expect. The floor beneath you holds its shape. Time moves forward at a familiar pace, marked by small changes you barely notice. The solar system, as you understand it, is distant and orderly. Mercury is a small, airless rock close to the Sun, long ago categorized and set aside as simple. That assumption is supported by decades of measurements, orbital mechanics, and thermal models that agree with one another. And yet, recent observations from the James Webb Space Telescope show Mercury behaving in ways that do not fit cleanly inside those expectations. Nothing dramatic appears to happen. Nothing explodes or shifts suddenly. The measurements are calm, repeatable, and internally consistent. What is unsettling is that they imply Mercury is not as passive, not as finished, and not as inert as your models require it to be. The contradiction is not loud, it is quiet, and it forces a question that does not stay confined to Mercury itself. 1. A planet you thought was understood. You begin with the assumption that Mercury is the most predictable planet in the solar system. It has no substantial atmosphere, no weather, no plate tectonics. Its proximity to the Sun explains its heat, its density, and its surface scars. This picture has been stable for decades. But the first Webb measurements do not add detail to this picture. They interfere with it. They show activity where stillness was expected, and variation where equilibrium should have already been reached. You were taught to think of Mercury as finished. Its formation ended early, its interior cooled quickly. Its surface was shaped by impacts, then locked in place. Compared to planets with clouds, oceans, or shifting crusts, Mercury appeared simple. Its behavior could be reduced to distance, mass, and sunlight. Once those parameters were set, the rest followed predictably. That assumption has underpinned mission planning, thermal models, and surface evolution theories for generations. The logic behind that confidence was sound. Mercury is small. Small planets lose internal heat rapidly. Without internal heat, there is no sustained volcanism, no tectonic recycling, no atmospheric replenishment. With no atmosphere to redistribute energy, temperature differences should be extreme, but mechanically trivial. The planet should bake and freeze in place, repeating the same cycle endlessly without accumulating meaningful change. What Webb introduces is not a dramatic violation of those principles. Instead, it reveals their incompleteness. When Webb measures Mercury in infrared wavelengths, it detects thermal behavior that does not fully settle into the expected pattern. Certain regions retain heat longer than surrounding terrain. Others release it more efficiently than models allow. The differences are subtle, but they persist across observations. They do not average out. Persistence is the key issue. Random variation would be noise. Instrument error would be inconsistent. But Webb's data is stable. The deviations repeat. That means the surface is not behaving as a uniform boundary layer. It is interacting with energy in ways that depend on composition, structure, and exposure history. Mercury's surface is not just present, it is participating. This forces you to reconsider what predictability actually means. A predictable system is not one that never changes. It is one whose changes can be fully accounted for by known variables. Mercury's changes cannot be dismissed as minor once they accumulate consistently outside prediction. The planet remains simple only at resolutions that ignore these interactions. The contradiction deepens when you consider time. Mercury has existed for billions of years. Any imbalance between energy input and output should have resolved long ago. Thermal gradients should have flattened. Chemical heterogeneity should have diminished. The fact that Webb observes ongoing variation implies that Mercury is maintained in a state of low-level disequilibrium. Not violently, not catastrophically, but continuously. 2. The telescope that was not meant for Mercury. You assume the James Webb Space Telescope is designed to look outward, toward cold and distant objects. Its instruments are tuned for faint infrared signals, not for a sunlit rock nearby. And yet Webb can observe Mercury precisely because of that sensitivity. When it does, it detects thermal patterns and spectral signatures that earlier instruments could not isolate. The contradiction begins with the fact that Mercury reveals more when seen in wavelengths meant for the deep universe. Webb was built to detect what barely emits. Its mirrors and detectors are optimized for objects whose light has been stretched by distance and time. In that context, Mercury should be an inconvenience. It is close, bright, and flooded with solar radiation. Pointing an infrared observatory at such a target risks saturation, noise, and contamination. For most of its design life, Mercury was not a priority, and in some configurations, it was actively avoided. Yet the very qualities that make Webb unsuitable for casual planetary observation are what allow it to detect what other instruments could not. Webb does not simply see brightness. It measures how energy is distributed across precise infrared wavelengths. It does not look for shapes alone, but for patterns of emission that encode temperature, composition, and physical state. Mercury, when viewed this way, stops looking uniform. Earlier missions saw Mercury in visible light and limited infrared bands. They mapped craters, measured average temperatures, and confirmed broad trends. Those observations supported a simplified model: extreme heat in sunlight, extreme cold in shadow, with sharp transitions between the two. Webb's instruments break that assumption by resolving gradients within those extremes. Heat is not only present or absent, it lingers, shifts, and leaks. Infrared observation turns temperature into a tracer. Every surface emits energy according to its structure and composition. Webb detects slight delays in cooling and unexpected retention of warmth. These effects are not large enough to matter in everyday terms, but they matter because they are systematic. They indicate that Mercury's surface interacts with solar energy in ways that are not spatially uniform. The contradiction is not that Mercury is hot. That was never in doubt. The contradiction is that its heat behaves as if the surface has memory. Regions exposed to sunlight respond differently depending on their history, not just their position. This implies variations in grain size, porosity, or subsurface layering that were assumed to have been erased by time. Webb also isolates spectral signatures that hint at chemical diversity across Mercury's surface. In visible light, these differences blur together. In infrared, they separate. You are not seeing new substances appear. You are seeing known substances behave differently under stress. The planet becomes chemically textured rather than chemically averaged. This raises an uncomfortable point about instrumentation. What you know about a system depends not just on its properties, but on how you choose to observe it. Mercury did not change when Webb looked at it. The observational framework changed. A telescope meant to study the earliest galaxies is revealing unresolved complexity in the nearest rocky planet. That inversion matters. It suggests that some planetary behaviors only become visible when observed outside their intended context. Mercury reveals its anomalies not when treated as a geological body, but when treated as a radiative system. Webb does not ask what Mercury looks like. It asks how Mercury exchanges energy with its environment. 3. Heat that does not settle. You expect Mercury's surface temperature to follow a simple rule: extreme heat on the day side, extreme cold on the night side, repeating endlessly. Webb's infrared data shows this is only approximately true. Some regions retain heat longer than models predict, others cool too quickly. The energy balance is off by small amounts, but those amounts persist. That persistence is the problem. The simplicity of Mercury's thermal model has always been its appeal. With no atmosphere to transport heat and no oceans to store it, surface temperature should be governed almost entirely by sunlight and rotation. When the sun rises, the ground heats rapidly. When it sets, the ground radiates that heat away just as quickly. Over many cycles, any irregularities should cancel out. The planet should behave like a bare object placed in space, responding instantly and forgetfully to illumination. Webb's measurements undermine that forgetfulness. Infrared data shows that Mercury does not release energy uniformly once sunlight is removed. Some terrains remain warmer longer into the night than their surroundings. Others shed heat faster than expected, becoming colder earlier than models allow. These are not transient fluctuations. They repeat from orbit to orbit, implying a structural cause. To understand why this matters, you have to consider what temperature represents at this scale. Temperature is not just how hot something is. It is a record of how energy moves through matter. If heat lingers, it means energy is being stored. If it vanishes too quickly, it means energy is escaping through pathways not accounted for. On Mercury, those pathways should be limited and well understood. The common explanation for thermal variation is material difference. Fine dust insulates, solid rock conducts. Porous surfaces trap heat. Dense ones release it. Over billions of years, you would expect Mercury's surface to become a blended average of these states. Impacts churn material. Micrometeorites garden the regolith. Extremes should smooth out. The fact that they have not suggests that Mercury's surface is stratified in ways that resist mixing. Beneath the visible regolith may lie layers that redirect heat downward or sideways instead of outward. Webb's data does not show you these layers directly, it shows you their effect. The surface behaves as though it is coupled to something deeper and more complex than a thin blanket of dust. This introduces a contradiction in scale. Mercury is too small to retain internal heat in the way larger planets do. Its core should no longer influence surface temperature meaningfully. And yet the thermal inertia implied by Webb's observations hints at subsurface structures that still matter. Not as sources of heat, but as regulators of its flow. Another possibility is that the surface itself is changing continuously. Solar radiation alters grain size, chemistry, and texture over time. These changes affect how heat is absorbed and released. If sunlight is constantly modifying the surface, then equilibrium is never reached. The system is always adjusting to conditions that shift slightly faster than averaging can occur. What makes this unsettling is not the magnitude of the effect, but its direction. Mercury is not trending toward uniformity. It is maintaining difference. The planet's rotation, orbit, and exposure are stable. The input conditions are consistent, yet the output remains uneven. 4. A surface that behaves like a system. You usually think of a planetary surface as a boundary. On Mercury, Webb suggests it behaves more like an interface. Heat moves through it unevenly, implying subsurface structures or compositions that have not homogenized over billions of years. This contradicts the assumption that Mercury's interior reached thermal simplicity long ago. A boundary is something you measure across. An interface is something you measure through. The difference matters. In most models, Mercury's surface is treated as the end of meaningful interaction. Energy arrives, energy leaves, and what lies beneath is largely irrelevant on observable timescales. Webb's data erodes that distinction. The surface is not just responding to sunlight, it is mediating between external energy and internal structure. When heat distribution varies consistently across terrain, it implies that the surface is coupled to what lies below it. This coupling does not require active volcanism or internal heat generation. It only requires pathways through which energy can move differently in different places. Those pathways persist only if the interior has not fully blended into a uniform state. The assumption of interior simplicity comes from Mercury's size and age. Small bodies cool fast. Once cooled, their interiors become mechanically quiet. Without convection or melting, structures should relax and differences should diminish. Over billions of years, Mercury's subsurface should have become predictable and inert. Webb's observations imply otherwise. The surface does not behave as if it sits atop a homogeneous interior. Instead, it behaves as if it overlays a patchwork. That patchwork may consist of ancient lava flows, impact-modified layers, or chemically distinct zones preserved beneath the regolith. Whatever their origin, they still influence how energy moves today. This reframes Mercury's surface from a static shell into an active filter. Incoming solar energy is not simply absorbed and re-emitted, it is redirected, delayed, or conducted inward, depending on local conditions. The surface participates in energy transport rather than marking its termination. What makes this uncomfortable is that these effects should have been erased. Impact gardening, in particular, is thought to mix surface materials effectively over time. Countless small collisions churn the regolith, breaking up structure and blending composition. If that process were complete, the thermal behavior Webb sees would not persist. The persistence implies limits to mixing. Either the depth of influence extends beyond what impacts disturb, or the underlying structures regenerate their thermal signature despite surface disruption. In both cases, the surface cannot be treated as a thin, forgetful layer. Thinking of the surface as a system changes how you interpret observation. A system has internal relationships. Its parts influence one another over time. Mercury's surface appears to remember where it has been exposed, how it has been altered, and what lies beneath it. That memory expresses itself as uneven heat flow. This also changes how you think about scale. The differences Webb detects are not global. They are local, sometimes subtle and easy to miss when averaged. But systems do not require large contrasts to function. They require persistent ones. Mercury's surface exhibits just enough structure to remain out of equilibrium without becoming unstable. The deeper implication is that simplicity may be an observational artifact. When you lack resolution, boundaries appear sharp. When you gain it, boundaries dissolve into transitions. Mercury was once categorized as simple because your instruments could not see past its surface behavior. Webb reveals that the surface itself is not a single thing. You are left with a planet whose outermost layer cannot be treated as the end of the story. It is a conduit. It translates solar energy into internal response, even in a body long assumed to be thermally finished. Mercury does not contradict physics. It exposes how much physics can remain active even after you believe the system has stopped changing. 5. An atmosphere that should not count, A Mercury has an exosphere, not a true atmosphere. It is thin, transient, and often ignored. Webb detects its components with unusual clarity, revealing spatial and temporal variations. These changes are measurable and structured. An atmosphere that should be negligible is behaving like something that responds, adapts, and redistributes material. An atmosphere, as you normally understand it, is a continuous layer of gas dense enough for collisions between particles to matter. Mercury does not have that. Its exosphere is so sparse that atoms rarely interact with one another. Each particle follows its own trajectory, governed more by gravity, sunlight, and magnetic fields than by neighboring atoms. In theory, this makes the exosphere simple. It should be a statistical cloud, not a dynamic system. Webb's observations challenge that expectation. By isolating specific infrared signatures, the telescope detects variations in exospheric composition across Mercury's surface and over time. These variations are not random. They correlate with illumination, local surface properties, and interaction with the solar wind. The exosphere behaves as if it has structure, even though it lacks the density required for conventional atmospheric processes. To understand why this matters, you have to abandon the idea that interaction requires contact. In Mercury's environment, sunlight and charged particles supply the coupling. When photons strike the surface, they eject atoms into ballistic trajectories. When solar wind particles interact with the magnetic field, they funnel energy into specific regions. The exosphere is continuously rebuilt from the surface below. This creates a feedback loop. Surface composition influences which atoms are released. Released atoms alter the local exospheric density. That density affects how energy and particles interact with the surface in the next cycle. No individual atom participates for long, but the pattern persists. The system maintains coherence without continuity. The unsettling part is that this coherence is detectable. Webb does not see a smooth halo of gas. It sees gradients. It sees enhancements and depletions tied to local conditions. An atmosphere that should average itself out instead reflects the planet's heterogeneity back into space. This forces you to reconsider what it means for something to count. The exosphere is too thin to support weather, pressure, or sound. It cannot store heat or transport energy in bulk, yet it participates in material redistribution. Atoms lifted from one region may land in another. Some escape entirely. Others return altered by radiation. Over long timescales, this process reshapes the surface. Volatile elements migrate. Certain regions become depleted while others accumulate residues. The exosphere acts as a conveyor, not a container. Its influence is slow, but it never stops. Webb's clarity makes this unavoidable. When variations persist across observations, they imply stability of pattern, not of individual particles. The atmosphere does not exist as a thing. It exists as a process. That process is structured enough to be measured. This complicates the traditional hierarchy of planetary features. Atmospheres are usually treated as major or minor based on density. Mercury's exosphere defies that classification. It is minor in mass, but major in consequence. Its effects are disproportionate to its presence. 6. Sodium, potassium, and motion. You are familiar with sodium tails observed on Mercury from Earth. Webb refines these observations, showing how elements migrate across the planet's surface and into space. The motion is not random. It follows patterns driven by solar radiation and magnetic interaction. The unsettling detail is that Mercury is actively sorting its own material. For years, ground-based telescopes have detected extended clouds of sodium trailing Mercury like a faint comet tail. These observations were striking, but limited. They showed that atoms could be lifted from the surface and pushed away by sunlight. What they could not show clearly was where those atoms originated, how they moved across the surface before escape, or how tightly that motion was coupled to Mercury's environment. Webb changes that. Its sensitivity allows it to track variations in elemental emission with spatial precision. Sodium and potassium, both easily liberated by energetic processes, appear and disappear in regions that correlate with local conditions rather than global averages. The surface is not shedding material uniformly, it is doing so selectively. This selectivity matters because it implies control. Mercury is not simply losing atoms wherever energy happens to strike. The release depends on surface composition, grain structure, and exposure to solar particles. Regions rich in certain minerals release atoms more readily. Others resist. Over time, this differential release alters the surface itself. The driving forces are well understood in isolation. Solar radiation exerts pressure. Charged particles interact with magnetic fields. When combined, these forces impart momentum to atoms on the surface, sometimes enough to overcome gravity. What Webb shows is how organized the result becomes when these forces act continuously. Sodium and potassium do not drift aimlessly once released. Their trajectories are shaped by Mercury's weak magnetic field and by the direction of incoming solar wind. This creates preferred pathways for motion, concentrating material loss in some regions and accumulation in others. The planet develops chemical gradients without needing fluid flow or tectonics. This is not chemistry happening in a laboratory. It is chemistry enforced by exposure. The Sun provides energy. Mercury provides material. The interaction sorts elements according to how easily they respond. Over long periods, this acts like a filter, gradually changing the planet's outermost composition. The unsettling implication is that Mercury is not compositionally static. Even without an atmosphere capable of mixing, even without internal recycling, the planet reorganizes itself. Elements migrate. Some are preferentially removed, others remain behind. The surface evolves not through internal dynamics, but through sustained external forcing. This challenges the idea that geological change requires internal energy. On Mercury, change is driven from above. Radiation replaces convection. Particle impact replaces erosion. The sorting happens quietly, atom by atom, but it never stops. 7. The role of sunlight as a force. You usually treat sunlight as illumination and heat on Mercury. Webb's data reinforces that sunlight is also a sculpting mechanism. Photons strike the surface with enough energy to eject atoms directly into space. This is not erosion in the familiar sense. It is direct momentum transfer, and it never stops. In everyday experience, light is passive. It lets you see. It warms surfaces gradually. Its influence feels indirect. On Mercury, that intuition fails. The planet sits so close to the Sun that sunlight arrives not just as energy, but as impact. Individual photons carry momentum. When they strike exposed atoms on the surface, they can transfer enough of that momentum to dislodge them entirely. This process is known in principle as photon-stimulated desorption. It is not speculative. It has been measured in laboratories and inferred in space environments for decades. What Webb contributes is scale and clarity. The telescope shows that this effect is not marginal on Mercury. It is persistent, spatially structured, and cumulative. Unlike mechanical erosion, nothing is grinding the surface down. No particles scrape across rock. No fluid carries debris away. Instead, atoms are lifted one by one. A photon arrives. Momentum transfers. An atom escapes its binding and enters a ballistic trajectory. Multiply this by uncountable photons over uncountable time, and the surface slowly thins. The key difference is that this erosion has direction. Sunlight arrives from a specific angle. Its intensity changes with Mercury's orbit and rotation. As a result, some regions experience sustained particle loss, while others are partially shielded. The surface is not eroded evenly. It is patterned by exposure. Webb's observations support this by correlating elemental loss with illumination geometry. Regions that receive more intense or prolonged sunlight show enhanced signatures of liberated atoms. This is not a thermal effect alone. Even when temperatures are accounted for, the momentum carried by photons remains sufficient to alter surface composition. What makes this unsettling is how fundamental the mechanism is. There is no threshold event. No special condition needs to be met. As long as the sun shines, the process continues. Mercury cannot escape it. There is no equilibrium state where photon impact ceases to matter. This forces you to rethink the role of light in planetary evolution. Light is usually treated as an input variable, something that sets temperature. On Mercury, it is also an output driver, actively removing material. The sun is not just heating the planet, it is unbuilding it. The scale of the effect is slow enough to seem negligible. Over a year, nothing noticeable changes. Over 1,000,000 years, the loss is still subtle. Over billions of years, it becomes unavoidable. The planet's surface composition reflects not just formation and impacts, but continuous subtraction. This introduces a different kind of causality. Mercury is not reacting to rare events. It is responding to constant ones. The cause is always present. The effect accumulates quietly. There is no clear moment when change begins, only a record that shows it never stopped. Webb's sensitivity makes this visible by detecting the products of that momentum transfer. Freed atoms leave signatures. Their distribution maps back to regions of strongest exposure. The data does not dramatize the process. It confirms it with consistency. The implication extends beyond Mercury. Any airless body close to a star experiences this force to some degree. Mercury simply occupies an extreme where the effect cannot be ignored. It becomes a natural experiment in how light reshapes matter when nothing intervenes. You are left with a planet that is being sculpted by something you usually consider harmless. Sunlight does not need to burn, melt, or fracture rock to change it. It only needs to arrive, relentlessly. Mercury shows that even the most familiar force in your experience can act as a tool of gradual removal, operating continuously, without pause, and without ever announcing that it is doing so. 8. A planet that is slowly evaporating. The measurements imply that Mercury is losing material continuously. Not catastrophically, but persistently. Over human timescales, this loss is negligible. Over geological timescales, it is not. You are forced to confront a planet that is not simply weathered, but gradually disassembled by light itself. This is not the kind of evaporation you might imagine with water or ice. There is no boiling, no phase change triggered by heat alone. Mercury's evaporation occurs atom by atom, driven by sunlight, solar wind, and particle interactions. Individual atoms gain enough energy to escape the planet's weak gravity, entering space indefinitely. Over millions of years, the cumulative effect is measurable, even if imperceptible in a human lifespan. Webb's data makes this clear. It does not exaggerate. It records variations in elemental abundance above the surface, detecting sodium, potassium, and other volatiles leaving their source regions. These losses are structured. They correspond to areas receiving more radiation, areas where solar wind impacts are concentrated, and regions influenced by the magnetic field. Material is not lost randomly. It is selectively exported according to environmental conditions. The gradual removal of atoms transforms Mercury in ways that are easy to overlook. Surface composition changes subtly but continuously. Areas once rich in certain elements may become depleted, while more resistant materials persist. Over billions of years, these small redistributions produce a surface that is chemically distinct from the primordial rock. Mercury is not static. It is being edited, atom by atom, by the very energy that sustains it. This challenges the assumption that erosion or loss requires visible motion or activity. There is no dust storm, no river, no lava flow driving this change. Instead, sunlight, photons, and charged particles serve as silent agents, slowly disassembling the planet's outer layers. The processes are entirely natural, fully measurable, and relentless. Their subtlety is part of the problem. The planet appears inert while its mass is subtly diminishing. Over human observation, this effect is negligible. We measure variations of fractions of millimeters or grams, but Mercury has existed for over 4 billion years. Even minor losses, when accumulated over such vast spans, are profound. The planet has been evolving, not through dramatic upheavals, but through a slow, patient mechanism that quietly erases and redistributes its material. The unevenness of this process adds to its strangeness. Some regions lose atoms more rapidly than others. Thermal gradients, local composition, and exposure to sunlight create spatial patterns of depletion. Mercury's surface is, in effect, a filter that gradually sorts and exports its own material. Its features are not permanent monuments. They are snapshots in an ongoing sequence of subtle transformation. This realization forces a re-evaluation of how planetary evolution is measured. A planet does not need to erupt or collide to change fundamentally. Continuous, low-intensity processes can restructure it, provided the timescale is long enough. Mercury demonstrates that a planet's apparent stability can mask a profound dynamism occurring below the threshold of human perception. 9. Magnetic protection that is incomplete. You know, Mercury has a magnetic field, weak but real. It should offer partial protection from the solar wind. Webb's observations show that this protection is uneven. Some regions are shielded, others are exposed. The result is asymmetric interaction with the Sun, producing localized changes that accumulate. Mercury's magnetic field is orders of magnitude weaker than Earth's, but it is sufficient to divert charged particles in certain regions. For decades, this was assumed to reduce the effects of the solar wind uniformly across the planet, creating a broad zone of partial protection. In that view, surface weathering and particle ejection were predictable, defined primarily by latitude and exposure to sunlight. Webb's data reveals that this assumption is too simple. The telescope shows that solar wind impact varies across Mercury in ways that correspond directly to the configuration of its magnetic field. Some areas experience deflection, where charged particles skim along the field lines without striking the surface. Others lie in gaps, where the field is weak or disrupted, allowing particles to slam directly into the regolith. Over time, these variations produce measurable chemical and thermal differences across the landscape. The asymmetry is persistent. Unlike random micrometeorite impacts or transient events, the pattern repeats consistently with the planet's rotation and orbital position. Certain latitudes, certain craters, and even specific slopes are exposed to more energy, while others are effectively shielded. The magnetic field does not simply reduce solar wind uniformly, it channels it, creating pockets of concentrated effect. This uneven protection has direct consequences for Mercury's surface evolution. Atoms dislodged by solar wind or sunlight escape preferentially from exposed regions, while shielded areas retain more material. Over millions of years, this produces gradients in surface composition, subtle variations in volatile depletion, and localized thermal differences. Mercury is not just losing material, it is sorting it according to the geometry of its magnetic environment. The phenomenon also highlights a different principle. Protection is conditional. The magnetic field reduces risk in some areas but amplifies differences between regions. In doing so, it makes Mercury less uniform than it would be if no field existed at all. Shielding is not a passive blanket, it is a selective filter. It does not preserve the planet equally, it imposes structure on what would otherwise be random distribution. Webb's sensitivity allows you to see the consequences of this selective protection. Spectral signatures of sodium, potassium, and other light elements correlate with magnetically exposed areas. Thermal anomalies align with magnetic topology. The surface is not reacting randomly. It is responding to the interplay between sunlight, particle flux, and magnetic shielding. 10. A surface that remembers exposure. You expect ancient surfaces to average out their histories. Webb suggests Mercury's surface retains memory. Regions exposed differently to solar particles develop distinct chemical signatures. This means the planet records not just impacts, but directional exposure to space itself. On most planets, repeated processes tend to erase individuality. Lava flows cover older terrain. Wind and water redistribute sediments. Ice and weathering mix layers over time, producing surfaces that appear averaged, uniform, and forgetful. Mercury has none of these mechanisms. Its surface is airless, dry, and mechanically inactive. You would expect that, over billions of years, repeated bombardment and micrometeorite impacts would have homogenized its outer layer, leaving little trace of directional exposure. Webb's observations show this assumption is incomplete. The telescope reveals subtle chemical gradients correlated with historical illumination and solar wind exposure. Sodium, potassium, and other volatile elements are depleted or concentrated depending on whether a region has faced persistent solar radiation or particle flux. Craters, slopes, and ridges become long-lived markers of interaction. The planet retains a map of its own exposure, recorded in atomic shifts invisible to the naked eye, but measurable in infrared. Memory, in this context, is not conscious. It is structural. Mercury's surface holds a record because processes that could erase differences are weak or absent. Impact gardening occurs, but only partially. Thermal diffusion smooths temperature extremes, but not enough to homogenize chemical signatures. Photon-stimulated desorption removes atoms selectively. The interplay of these processes imprints a history onto the regolith, preserving the path of exposure across time. This has implications for how you perceive planetary surfaces. Mercury's crust is not passive. It is an archive. It does not simply bear scars from catastrophic events. It accumulates evidence of persistent, directional forces. Every atom that remains, every one that is displaced, encodes the history of sunlight, solar wind, and magnetic influence. In effect, the surface is a ledger, constantly updated, never erased completely. The effect is scale-dependent. Small deviations in solar incidence, local topography, or particle flux leave lasting chemical fingerprints. These differences are minute over human timescales, but over millions or billions of years, they become pronounced. Mercury's surface does not need dramatic upheaval to record change. Subtle, continuous processes are enough to encode memory into its chemistry and structure. This challenges conventional ideas about planetary stability. You tend to assume that ancient surfaces are inert, that history is averaged away by time. Mercury demonstrates that the absence of active erasure mechanisms allows memory to persist. What you see is not just a static rock. It is a repository of interactions, a record of forces applied in particular directions across geological time. 11. Hollows that should not persist. Mercury's surface contains shallow depressions known as hollows, believed to form from volatile loss. Webb's thermal sensitivity suggests these features may still be active. If true, Mercury is not only a record of past loss, but a site of ongoing transformation, long after its formation should have ended such processes. Hollows are striking precisely because they are anomalies on an otherwise ancient surface. Most craters, ridges, and plains on Mercury date back billions of years, frozen in their final forms. By contrast, hollows appear fresh, with sharp edges and bright interiors, suggesting recent activity. For decades, their existence posed a question: how could a planet so small, so long cooled, continue to produce surface changes without internal heating or atmospheric weather? Webb's data now provides an answer that is subtle yet profound. The process never fully stopped. Webb's infrared measurements reveal temperature variations within hollows that are inconsistent with surrounding terrain. These anomalies indicate that material is being released or rearranged in ways that cannot be explained by passive cooling alone. Heat retention and escape patterns differ from what models predict for old, inert surfaces, suggesting that volatile loss, evaporation of elements such as sulfur or sodium, continues to shape these depressions today. The persistence of hollows challenges assumptions about Mercury's thermal and chemical history. Traditional models suggest that small planets should lose their volatiles early in formation, leaving the crust chemically inert. Surface features are expected to reflect events that occurred billions of years ago, not processes that persist under current solar exposure. Webb shows that this is incomplete. Mercury remains chemically dynamic at the microscopic scale, even in a planet whose bulk evolution should be long finished. 12. Volatiles where heat should destroy them. You assume extreme heat eliminates volatile compounds. Webb complicates this assumption by detecting signatures consistent with volatile-bearing materials in unexpected regions. The implication is not that Mercury is cool, but that heat alone does not dictate chemical survival. Traditional models of Mercury emphasize the planet's proximity to the Sun and the resulting thermal extremes. Daytime surface temperatures can exceed 430 degrees Celsius, enough to vaporize most volatile elements and compounds. Nighttime, by contrast, plunges to nearly -180 degrees Celsius, but this cold cannot restore what is lost. Volatiles should have long since been driven off or chemically altered. Their presence in measurable quantities challenges that expectation. Webb's infrared instruments detect subtle absorption features that correspond to volatile-related chemical bonds. These are not random signals or noise artifacts. They repeat across multiple observations, spatially correlated with topographic features and shadowed regions. The distribution is uneven. Some areas retain volatiles while others are effectively barren. Mercury is not uniformly inhospitable to these materials, suggesting that local conditions modify the expected outcomes of heat exposure. The persistence of volatiles implies protective mechanisms at work. One factor is microtopography. Hollows, crater floors, and depressions can shield surface material from direct solar irradiation. Even slight shading alters the thermal regime enough to preserve compounds that would otherwise volatilize. In these niches, chemical bonds survive longer, producing the signals Webb detects. Subsurface structures also contribute. Mercury's regolith may act as a thermal buffer. Layers of dust, rock, and ancient lava flows can insulate volatiles embedded beneath the surface. Heat propagates downward unevenly, leaving pockets where atoms are trapped or released only slowly. These microenvironments allow the long-term persistence of materials in a setting where they should be transient at best. The implication extends beyond physical shielding. Mercury's weak exosphere and continuous surface sputtering redistribute material in patterns that reinforce volatile retention. Atoms released from one location may recondense in another, particularly in areas less exposed to solar photons or charged particles. Over millions of years, this process creates a quasi-equilibrium in which volatiles are continuously cycled rather than permanently lost. This challenges the simplistic equation of temperature with chemical fate. Heat is influential, but it does not act alone. Energy interacts with structure, particle flux, and surface composition to produce outcomes that are both predictable in principle and counterintuitive in practice. Mercury demonstrates that environmental extremes cannot be interpreted in isolation. They produce complex, emergent behaviors in materials. 13. A planet out of chemical equilibrium. The data points toward Mercury existing in a state of long-term imbalance. Material is constantly moved, altered, and removed, yet the system does not settle. You are looking at a planet that never reaches the quiet end state your models predict. Chemical equilibrium is usually an organizing principle in planetary science. Over time, materials redistribute until reactions cease, volatile elements are lost, and compositions stabilize. On Mercury, however, this expectation fails. Webb's measurements show that volatile compounds persist unevenly. Surface atoms migrate, and thermal behavior varies regionally. The planet is not approaching stasis. It is continuously reorganizing itself at a microscopic level. The imbalance begins with the movement of atoms across the surface. Sodium, potassium, and other volatiles are liberated by sunlight, solar wind, and photon-stimulated desorption. Some escape entirely into space, while others redeposit locally, creating subtle gradients in composition. These gradients do not average out over time. Instead, they persist, layered upon one another, forming chemical mosaics that reflect continuous input and removal. Temperature contributes to this disequilibrium. Mercury's extreme day-night cycle imposes rapid thermal swings that affect energy distribution in the surface. Webb detects regions that retain heat longer or release it faster than models predict, suggesting interactions with subsurface layers. These variations influence the chemical behavior of elements, altering reaction rates and migration patterns in ways that prevent uniformity. Thermal extremes are not merely environmental, they are drivers of ongoing chemical activity. The planet's magnetic field introduces another dimension. Its uneven shielding creates asymmetric exposure to the solar wind. Charged particles preferentially strike some regions, eroding atoms in concentrated areas while leaving others relatively untouched. This selective bombardment reinforces chemical heterogeneity, turning Mercury's surface into a system that reacts differently depending on location. The result is persistent disequilibrium, maintained by forces you might have assumed would lead to averaging rather than differentiation. 14. Time as a misleading scale. You tend to think in human or geological time. Webb forces you into intermediate scales, where slow processes matter. Mercury's changes are too gradual to feel dramatic, but too consistent to ignore. This challenges your sense of when change becomes meaningful. Human perception is calibrated to notice abrupt events. A volcanic eruption, a meteor strike, or a sudden thermal shift grabs attention because it occurs within a span you can measure. Geological time, by contrast, compresses billions of years into abstract numbers, allowing you to assume that slow processes will average out, leaving a stable planetary surface. Mercury exposes a gap between these scales. Processes that are imperceptible in the short term, yet significant over intermediate spans, measured in centuries to millennia, which are often overlooked. Webb's infrared and spectroscopic observations highlight subtle, persistent variations in thermal and chemical properties. Sodium and potassium migrate across the surface. Volatiles concentrate in hollows and shaded regions. Thermal anomalies persist in localized patches. Each effect taken in isolation seems negligible. Over decades or centuries, however, these small motions accumulate into meaningful alterations of the surface and its chemistry. Mercury is changing in ways that are too slow to witness directly, yet too structured to dismiss as noise. 15. Measurement without catastrophe. Nothing in the data suggests an impending event. There is no explosion, no collapse. The discomfort comes from precision. The instruments are working correctly. The signals are clear. The implications emerge not from error, but from accuracy. You are accustomed to thinking of planetary drama as something sudden. A collision, a volcanic eruption, or a catastrophic loss of atmosphere is the type of event that captures attention. Mercury offers none of that. Webb does not detect imminent destruction. There is no observable failure, no dramatic instability, no irregularity that suggests the planet will change in the next moments. Yet, the very absence of catastrophe is part of what makes the observations unsettling. The data's precision is what reveals Mercury's subtle dynamism. Every thermal anomaly, every spectral signature of volatile atoms, every pattern of chemical redistribution is measurable, repeatable, and consistent. Webb confirms the presence of slow, continuous processes that do not manifest as explosions or fractures, but are no less consequential. The planet evolves quietly, persistently, and imperceptibly to casual observation. This precision forces a new way of understanding planetary behavior. You cannot dismiss small deviations or irregularities as statistical noise because Webb's instruments are capable of distinguishing true patterns from error. Sodium and potassium migration, differential heat retention, and localized volatile loss are all detected with a clarity that eliminates ambiguity. Mercury is systematically changing, yet these changes do not rise to the level of catastrophe. They exist in the realm of measured, predictable evolution. 16. Mercury as a boundary case. You begin to see Mercury not as an exception, but as a boundary condition. It occupies an extreme environment where subtle physical processes dominate. Understanding it forces you to confront how matter behaves when pushed just beyond familiar limits. In planetary science, most of your models are built around familiar scales. Earth-like conditions, atmospheres thick enough to mediate heat and chemistry, and gravity sufficient to retain most surface material. Mercury challenges each of these assumptions: its proximity to the Sun, its weak magnetic field, its near-absent atmosphere, and its extreme diurnal temperature swings create conditions at the edge of what you normally consider. Under these conditions, processes that are negligible elsewhere become dominant. Webb's observations reveal that Mercury's surface and exosphere are governed by mechanisms that rarely manifest in less extreme settings. Photon-stimulated desorption, selective volatile loss, and localized chemical differentiation occur not as anomalies, but as the natural outcome of Mercury's environmental parameters. The planet functions as a natural laboratory, showing you how energy and matter interact when constraints, gravity, temperature, exposure, are pushed to their limits. This boundary status is visible in the planet's chemical heterogeneity. Sodium and potassium migrate along defined paths, accumulating in some regions while depleting in others. Hollows continue to form and evolve. Thermal anomalies persist longer or dissipate faster than predicted. The weak magnetic field channels solar wind in patterns that reinforce chemical asymmetry. These effects are amplified by the planet's extreme environment. The same forces would be almost invisible on larger, more protected worlds. Mercury also highlights how subtle, cumulative effects can dominate long-term evolution. On Earth, dramatic events, volcanic eruptions, tectonic shifts, storms, overwhelm slow, incremental processes. On Mercury, incremental processes are the primary agents of change. The absence of atmosphere, oceans, or large-scale internal convection means that slow mechanisms acting persistently sculpt the planet's surface. Change is continuous, directional, and measurable. Yet it occurs without the visible drama you associate with planetary evolution. 17. What counts as geological activity? You usually define geological activity by volcanism or tectonics. Mercury shows activity without either. Its changes are driven by radiation, magnetism, and particle flow. This expands the definition of what it means for a planet to be active. Traditional definitions of geological activity rely on visible movement, molten rock flowing across a landscape, tectonic plates shifting, mountains rising, or craters forming. These are macroscopic events with immediate physical consequences. On Mercury, Webb reveals a different kind of activity, one that occurs at the atomic and chemical scale, driven by external forces rather than internal energy. The planet evolves continuously, but in ways that do not create visible upheaval. Photon-stimulated desorption is a primary driver. Solar photons strike surface atoms with sufficient momentum to dislodge them from the regolith. Over time, this generates directional loss, redistribution, and subtle reshaping of surface features. The process is slow, imperceptible in human terms, yet constant. It produces patterns in composition and topography that are persistent and measurable, yet would not register under conventional definitions of geological activity. Solar wind adds another layer. Charged particles strike the planet unevenly, sculpted by Mercury's weak magnetic field. Exposed regions experience selective erosion, while shielded regions retain material. This creates chemical and structural heterogeneity, analogous in effect to tectonic or volcanic differentiation, but without the associated mechanical disruption. The surface becomes a record of ongoing interaction with the space environment rather than the planet's interior. Thermal cycling contributes as well. Mercury's day-night extremes produce expansion and contraction of the crust, influencing the behavior of volatile compounds and the stability of regolith layers. These subtle effects interact with photon and particle-driven processes to maintain a persistent, low-level surface evolution. Temperature is not merely a background condition. It is a driver of change in a system that lacks more conventional geological forces. 18. The Sun as an agent, not a background. The Sun is often treated as a constant backdrop. Webb's Mercury observations frame it as an active participant. The Sun shapes planetary surfaces directly, not just through gravity and heat, but through continuous physical interaction. You are accustomed to considering the Sun primarily as a source of illumination, warmth, and gravitational binding. Its energy sustains planetary climates, drives weather cycles, and stabilizes orbits. Yet, on Mercury, Webb reveals a different relationship. The Sun is not passive. Photons, charged particles, and magnetic fields interact with the surface in ways that produce continuous, measurable change. Its influence is material, structural, and directional. Photon-stimulated desorption is one of the clearest examples. Solar photons strike surface atoms with sufficient energy to dislodge them from the regolith. Over time, this produces directional particle loss and redistribution. Sodium, potassium, and other volatiles are selectively ejected, leaving chemical gradients that map exposure history. These gradients are persistent, layered, and measurable, providing a record of the Sun's ongoing mechanical influence. The solar wind acts as a second, complementary mechanism. Streams of charged particles continuously bombard Mercury. The planet's weak magnetic field channels these particles unevenly, exposing some regions while shielding others. Atoms impacted in exposed areas gain momentum and escape, or are redistributed across the surface. These interactions are not episodic. They are constant, cumulative, and structured by the geometry of the planet's field relative to the Sun's particle flux. Even thermal input is more than a passive heating effect. Extreme day-night temperature cycles produce expansion and contraction, subtly mobilizing surface materials and influencing volatile stability. Mercury's surface does not merely respond to temperature changes, it is sculpted by them, with differential heating creating conditions for selective retention or loss of chemical species. The Sun's energy becomes a tool for planetary modification, not merely a background parameter. 19. A planet that never finished forming you. You assume planets finish forming early. Mercury's ongoing material redistribution suggests formation is not a closed chapter. Instead, it is a prolonged process, stretched thin but never concluded. Conventional models describe planet formation as a sequence of rapid, violent events. Accretion of material in a protoplanetary disk, collisions with planetesimals, and differentiation into core, mantle, and crust. By the time a planet stabilizes, billions of years of evolution are expected to smooth over most small-scale processes. Mercury, however, demonstrates that formation is not strictly an early event, but an ongoing phenomenon. continuously unfolding at scales invisible without precise instruments like Webb. The evidence lies in surface composition and structural behavior. Sodium, potassium, and other volatiles migrate across the planet, selectively concentrating and depleting regions over time. Hollows form and evolve, exposing layers of material previously thought inert. Thermal anomalies persist in ways that suggest subsurface structures are active participants in surface evolution. These features indicate that Mercury's outer layers are not fully settled. They continue to shift, rework, and reorganize, a process reminiscent of planetary differentiation. Even the planet's weak magnetic field contributes to this unfinished state. Solar wind interacts with exposed regions while leaving shielded areas intact. This selective bombardment redistributes matter asymmetrically, continuously modifying the surface. Each cycle of exposure and shielding subtly sculpts chemical and structural patterns, reinforcing the notion that Mercury's formation is not a discrete event, but a persistent, ongoing rearrangement. Thermal cycling adds another dimension. Extreme day-night variations expand and contract the crust, slowly mobilizing material and altering chemical stability. Over millennia, these micro-movements accumulate, revealing that planetary surfaces are not as rigid or final as classical models suggest. Mercury's surface records billions of years of incremental change, yet it continues to evolve in real time, a laboratory for observing formation processes at the smallest scales. Volatile retention further complicates assumptions about planetary completion. Traditional models predict that small, hot planets should lose most of their volatile content early, leaving a chemically inert crust. Webb reveals that pockets of volatiles persist, often concentrated in hollows or shadowed regions. These residual materials indicate that chemical differentiation and redistribution are not entirely concluded, providing a continuous thread of formation long after the initial violent phase. 20. Stability as an approximation. Mercury looks stable from a distance. Webb shows that stability is an approximation dependent on scale. At finer resolution, the planet is restless. This forces you to question how often stability is merely the absence of sufficient measurement. From Earth, Mercury appears as a static, cratered world, locked into its orbit and largely unchanging over human lifetimes. Its surface seems frozen, ancient, and chemically inert. Early observations reinforced this impression, suggesting a planet that had long since reached equilibrium. Webb's instruments challenge this assumption. When observed with extreme sensitivity, every detail of Mercury reveals movement, change, and persistent interaction with energy sources that were previously invisible. Thermal patterns alone illustrate the point. Temperature measurements across the surface do not conform to the simple day-night extremes predicted by basic models. Some regions retain heat longer than expected, others cool more rapidly. At first, these deviations appear minor, almost negligible. Yet when measured precisely, they are systematic and consistent, forming persistent patterns that slowly influence surface and subsurface behavior. Stability is revealed to be conditional, dependent on the resolution and duration of observation. Chemical distribution amplifies this insight. Volatiles, once thought entirely lost to early planetary processes, are present in small but measurable concentrations. Sodium and potassium migrate directionally across the surface, forming gradients shaped by photon-stimulated desorption, solar wind, and the weak magnetic field. Hollows continue to evolve, showing that material redistribution is ongoing. What seemed chemically uniform from afar is revealed to be heterogeneous, dynamic, and constantly reworked at fine scales. Even structural stability is illusory. Small depressions, ridges, and surface microfeatures respond to radiation, thermal cycling, and particle flux. Over centuries and millennia, these tiny changes accumulate, creating measurable modifications in surface topology. Mercury's appearance of permanence masks slow evolution. At macroscopic scales, the planet seems inert, but at micro and mesoscales, it is constantly responding to internal and external forces. This realization forces a reconsideration of planetary modeling. Stability is not an absolute state, but a relative one, emerging from the limits of observation. A planet appears stable if the forces acting upon it produce changes too small, too slow, or too subtle to be detected with available instruments. Webb's precision demonstrates that once measurement is sensitive enough, even the most apparently quiescent planets reveal dynamism. Stability becomes an artifact of resolution, not a fundamental property of the system. 21. Observation alters understanding, not reality. Nothing about Mercury changed when Webb observed it. Only your access to information did. This highlights an uncomfortable truth. Reality can remain unchanged while your understanding shifts beneath you. You assume that observation reveals reality in a simple, straightforward way. You look, measure, and record, expecting the world to present itself as it is. Mercury defies this assumption. Its surface, exosphere, and thermal behavior have existed in their current forms for millennia. The planet does not suddenly move or evolve faster when observed. Yet the precision of Webb's instruments transforms your perception, revealing processes and patterns that were always present but invisible to earlier measurement. Understanding lags behind reality, sometimes by decades, centuries, or millennia. The apparent simplicity of Mercury is deceptive. From Earth, it appears as a small, cratered world, chemically inert and thermally extreme, with a weak magnetic field and minimal atmosphere. Observations prior to Webb reinforced this image. Only now, with unprecedented sensitivity, do you perceive the subtle redistribution of surface atoms, the persistence of volatiles, the evolving hollows, and the localized thermal anomalies. All of these phenomena existed long before you could detect them. The planet's behavior is not dependent on your observation. It is your understanding that is reshaped. This distinction between reality and perception becomes especially clear when considering timescales. Processes that unfold over centuries or millennia, such as slow, volatile migration, gradual surface restructuring, or differential thermal retention, appear static until observed with sufficient precision. The planet has been evolving continuously, atom by atom, without pause. Observation does not initiate these changes. It merely illuminates them, allowing you to integrate discrete measurements into coherent patterns that were previously inaccessible. The chemical redistribution of sodium and potassium offers a concrete example. Earlier instruments detected these elements only in bulk averages, suggesting uniform depletion or loss. Webb, however, resolves the spatial and temporal gradients, revealing ongoing movement shaped by photon-stimulated desorption, solar wind, and magnetic shielding. The planet's atoms did not move differently because they were being observed. Your measurement now matches the subtle realities of Mercury's persistent dynamics. Thermal behavior illustrates the same point. Nighttime cooling and daytime heating are neither uniform nor instantaneous. Webb identifies variations that deviate from predicted extremes. Small regions retain heat longer or release it more quickly, creating patterns that had existed unnoticed for eons. Observation does not generate these anomalies, it only makes them perceptible, forcing a reassessment of previously accepted models. The planet has always been restless. Only now are you equipped to see it. The broader implication is philosophical as well as scientific. Observation does not create reality. It adjusts your mental model. Knowledge accumulates incrementally, and each layer may reveal contradictions or complexities hidden beneath prior assumptions. In the case of Mercury, every new measurement uncovers persistent activity and subtle forces that challenge established definitions of stability, equilibrium, and planetary evolution. The universe continues independently of human awareness, indifferent to whether its mechanisms are understood. Mercury exemplifies how understanding is provisional. You perceive a planet as static, inert, or finished until instruments allow finer resolution. Each enhancement of observation reveals new structure, pattern, and activity, forcing you to reinterpret the same unchanging world. Precision does not alter the system, it alters the framework within which you comprehend it. You are confronted with the disquieting notion that reality operates continuously and fully, whether or not it is perceived. Your access to information determines the richness of interpretation, not the existence of phenomena. Mercury existed long before Webb, yet it now appears dynamic, restless, and subtly evolving. Observation exposes the planet's hidden activity, but it does not intervene or accelerate it. Reality persists in its complexity, indifferent to the observer, while your understanding must continually adjust to match it. In this sense, Mercury teaches a profound lesson. The universe is complete, continuous, and indifferent. Observation illuminates, clarifies, and refines understanding, but it never creates. Reality remains constant. Even as the landscape of comprehension shifts beneath you, revealing a world far more intricate and active than your earlier assumptions allowed. 22. A quiet failure of simplification. You prefer simple models because they work most of the time. Mercury demonstrates where they fail quietly, not with contradictions that break equations, but with residuals that refuse to disappear. Scientific models rely on simplification. By ignoring minor variables, averaging over space and time, and assuming equilibrium where possible, you produce predictions that are accurate enough for most practical purposes. Mercury seems like a candidate for such treatment. Small, old, apparently geologically and chemically inert. Yet Webb reveals that the planet is composed of persistent deviations, small, systematic, and continuous, that evade simple categorization. These are not catastrophic failures of theory. They are residuals, subtle misalignments between expectation and observation that accumulate over time. Thermal anomalies are a primary example. Standard models predict day-night temperature extremes that are nearly uniform across latitudes and longitudes. Webb's data shows otherwise. Certain regions retain heat longer or cool faster than predicted, producing small, consistent deviations from the expected thermal equilibrium. These residuals are tiny on any given day, almost imperceptible in casual observation, but persistent across decades and centuries. The system is not chaotic, it is quietly inconsistent with your simplified assumptions. Chemical redistribution adds another layer of subtlety. Sodium, potassium, and other volatiles migrate in patterns shaped by photon-stimulated desorption, solar wind, and localized magnetic shielding. Traditional models predict near-complete volatile loss and uniform distribution. Webb demonstrates gradients, local accumulations, and directional flows that persist over geological timescales. The discrepancies are not dramatic enough to invalidate the equations, yet they refuse to vanish. Mercury's surface quietly retains a record of continuous redistribution that simple models cannot fully account for. Even structural features reflect this quiet complexity. Hollows, depressions, and crater floors evolve subtly, their depth, composition, and thermal behavior shifting incrementally. Surface roughness interacts with radiation, particle flux, and thermal gradients, producing localized variations that maintain themselves over millennia. None of these changes demand dramatic upheaval. They are slow, persistent, and cumulative, precisely the kind of deviations that elude coarse simplifications. This persistence has implications for understanding planetary evolution. Simple models assume that small-scale deviations average out over time, producing equilibrium. Mercury suggests otherwise. When multiple subtle effects operate continuously, thermal retention, chemical migration, directional erosion, magnetic asymmetry, they can produce long-term patterns of disequilibrium. The residuals do not disappear. They compound, creating measurable divergence from any simplified prediction. The failure of the model is quiet, almost invisible, yet unavoidable under scrutiny. Even time contributes to the subtlety. Changes unfold at intermediate scales, too slow to notice in a human lifetime, but too consistent to ignore over centuries or millennia. Each incremental movement of an atom, each small alteration in thermal retention, each minor redistribution of volatiles contributes to the quiet persistence of Mercury's deviation from simplified expectations. Stability and equilibrium are illusions imposed by insufficient resolution and temporal sampling. Webb's observations make these residuals visible without exaggeration. They are not errors, anomalies, or glitches. They are part of the system. Mercury is internally consistent, yet systematically misaligned with the assumptions that underpin simplified models. It demonstrates that complexity need not be chaotic, and that the quiet persistence of small deviations can accumulate into patterns that challenge predictive frameworks. You are confronted with the unsettling notion that simplification is provisional. Models work because they ignore subtle realities, but those realities do not disappear. They persist, quietly reshaping your understanding as precision improves. Mercury is a laboratory for observing the limitations of simplification. A planet that appears static, stable, and finished until carefully measured, revealing persistent residuals that quietly defy easy explanation. In the end, Mercury shows that failure of simplification does not arrive with dramatic contradictions. It arrives softly, in persistent deviations, in chemical gradients that linger, in thermal anomalies that refuse to conform, and in structural features that evolve imperceptibly. The planet remains stable enough to be studied with confidence, yet complex enough to challenge the assumptions upon which that confidence depends. Stability is approximate, equilibrium is conditional, and simplicity, though convenient, is provisional. 23. Extending the implication beyond Mercury. If Mercury behaves this way under extreme conditions, you must consider where else similar processes operate unnoticed. The solar system may contain more gradual transformations than you have accounted for. Mercury is not unique in being exposed to intense radiation, solar wind, and a lack of atmospheric buffering. other inner planets, moons, and even asteroids experience persistent energy fluxes and particle interactions, though often less extreme. The processes that drive subtle chemical migration, volatile redistribution, and thermal anomalies on Mercury are not exclusive to it. They may be present wherever matter is exposed to sustained directional forces over long timescales. Your models often ignore these effects because they are slow and small, but Webb demonstrates that accumulation over centuries or millennia produces measurable evolution. Take the Moon, for example. Like Mercury, it has a weak or absent atmosphere, a surface exposed directly to solar radiation and the solar wind, and a crust that records billions of years of impacts. Could similar mechanisms, photon-stimulated desorption, directional volatile migration, thermal retention anomalies, be quietly altering lunar soil? If Mercury's processes operate there, the Moon may be more chemically and thermally dynamic than previously assumed, even though no dramatic geological events occur. Asteroids present another case. These small, irregular bodies are constantly exposed to solar photons and charged particles. Over long periods, they may evolve surface features, chemical gradients, or thermal properties without ever experiencing collisions large enough to attract notice. Mercury shows that subtle interactions with energy sources and space weather can drive long-term evolution, suggesting that the apparent stasis of these objects may be an illusion. Their surfaces may quietly shift and adapt on timescales invisible to casual observation. Even Mars, which has a thin but substantial atmosphere and a weak magnetic field, may experience analogous, though moderated, processes. Photons and particles still interact with its surface, driving chemical changes, dust migration, and volatile redistribution. The cumulative effects may be too slow to detect over human lifetimes, but over geological timescales, they could contribute to subtle but measurable evolution of the regolith, surface chemistry, and even near-surface thermal properties. Mercury serves as a template, showing what to look for in environments where the forces are smaller or partially mitigated. This perspective also reshapes assumptions about planetary stasis and equilibrium more broadly. You are trained to identify dramatic events, volcanism, tectonics, impacts, as the main agents of change. Mercury demonstrates that slow, persistent processes operating continuously can be equally significant over long timescales. Subtle activity, cumulative and directional, can quietly sculpt chemical, thermal, and structural properties across the solar system without producing immediately obvious evidence. Observational limitations have created a bias toward visible drama, obscuring the steady hand of small, persistent forces. The implications extend to exoplanetary systems as well. Small rocky worlds orbiting close to their stars, or worlds with weak atmospheres, may be undergoing similar processes. Volatile retention, chemical migration, and thermal evolution could be ongoing even in environments considered static. Webb's observations remind you that apparent stasis is often provisional, dependent on the resolution of measurement and the sensitivity of instruments. Mercury is a lens, not an anomaly. It demonstrates that slow, continuous transformation is possible even on worlds traditionally classified as inert. Where measurement has not yet reached sufficient resolution, these processes may operate undetected. The solar system is not a collection of static bodies punctuated by rare cataclysms. It is a network of objects quietly evolving under persistent forces, each accumulating subtle changes over centuries, millennia, and longer. You are confronted with a broader question. How many planetary surfaces you considered unchanging are in fact in constant, imperceptible motion? Mercury forces you to acknowledge that the universe operates in ways that are both patient and relentless. The subtlety of these processes does not diminish their reality. It only masked them until the sensitivity of instruments like Webb revealed the quiet persistence of change. The solar system may be far more dynamic, chemically active, and structurally evolving than any previous observation allowed you to conclude. 24. Measurement as a source of unease. The discomfort does not come from mystery. It comes from clarity. Each measurement reduces uncertainty while increasing implication. You are not confused about what Webb sees. You are unsettled by what seeing it means. You are accustomed to thinking of data as a tool to confirm models, to reinforce understanding, and to provide reassurance that reality behaves as expected. Webb's observations do all of that, but in doing so, they produce an unexpected consequence. The more precisely you measure Mercury, the more clearly you see the persistent processes that defy simplified assumptions. The planet is not chaotic and it is not unobservable. It is precise, structured, and measurable. But in that very precision lies the unease. Consider thermal measurements. Day-night temperature swings are expected, yet Webb resolves persistent deviations. Certain regions retain heat longer than predicted. Others cool faster. The differences are small, but systematic and repeatable. These residuals are not anomalies or noise. They are precise fingerprints of ongoing processes. Each additional decimal place in measurement brings a new layer of insight, showing that Mercury is neither inert nor fully equilibrated. Stability was assumed. Now it must be reconsidered. The unease comes from realizing that what appeared orderly is quietly dynamic. Chemical distribution amplifies this discomfort. Sodium, potassium, and other volatiles do not merely exist. They migrate, redistribute, and concentrate in patterns shaped by solar photons, particle flux, and magnetic asymmetry. Hollows form and evolve, subtly reworking the surface. Each measurement confirms activity that is persistent, structured, and ongoing. The reality was always there, but only the instruments now reveal it with certainty. Knowledge sharpens the paradox. You understand exactly what is happening, and precisely because of that, it feels unnatural. This clarity extends to structural evolution as well. Minor depressions, surface roughness, and microtopography respond to persistent energy inputs. Thermal cycling, photon impact, and particle flux reorganize atoms over centuries and millennia. Each measurement quantifies what was previously invisible, exposing incremental transformation as an undeniable phenomenon. You are confronted with change that is neither dramatic nor sudden, yet continuous and directional. The measured processes are quiet but cumulative, producing evolution without spectacle. Observation also reframes your sense of scale. Small effects, imperceptible to earlier instruments, are now revealed as drivers of long-term change. Each data point represents an interaction between energy and matter that persists over vast timescales. Stability is provisional. Equilibrium is never absolute. The planet's apparent calm masks a web of subtle processes whose cumulative effects are unavoidable. Measurement does not create the effect, but it makes it unavoidable in your awareness. The unease is compounded by implication. Mercury is not an isolated case. If these processes operate quietly but continuously on Mercury, they are likely present elsewhere, on other planets, moons, and small bodies across the solar system. The universe is filled with subtle dynamics that only high-precision instruments can detect. Your prior confidence in the stasis of planetary surfaces is now provisional. Measurement sharpens clarity while simultaneously eroding the comfort of previous assumptions. In this sense, precision becomes unsettling. You are not confronted with mystery or speculation. You are confronted with a world whose behavior is known in detail and yet fundamentally counterintuitive. Mercury is structured, measurable, and precise, yet it defies the expectations of stasis and chemical equilibrium. Each new measurement eliminates ambiguity while amplifying the significance of slow, continuous processes, revealing a quiet dynamism that operates invisibly until instruments reveal it. You are left with the realization that understanding can be disquieting. The clarity provided by measurement exposes truths that are undeniable, measurable, and persistent, yet subtly destabilizing to your assumptions. Webb does not create unease through speculation or drama. It delivers precise, verifiable data. The unsettling truth is that the universe can be fully observed, fully understood in detail, and still remain quietly, inexorably, and fundamentally surprising. 25. The question that remains. You are left with a planet that is measurably active, persistently altered, and never fully at rest. The question is no longer what Mercury is doing, it is how many other parts of reality behave the same way, quietly, continuously, and only becoming strange once you measure them closely enough. Mercury forces a reconsideration of assumptions about planetary behavior. Until Webb, it seemed a world largely inert, a fossilized record of early solar system processes. The evidence now shows that activity is not always violent, dramatic, or immediately visible. Instead, it can be persistent, subtle, and continuous, occurring at scales previously dismissed as negligible. Each measurement of the planet, each incremental observation, reveals processes that have been ongoing for millennia, quietly reshaping surface features, redistributing chemical species, and modifying thermal patterns. This raises the broader question: how many other seemingly stable systems are similarly alive with imperceptible change? The solar system is filled with worlds that, like Mercury, experience continuous input of energy and matter. The Moon, Mars, Venus, and numerous asteroids are subject to sunlight, particle flux, and magnetospheric effects. Even worlds with atmospheres are not exempt. Their surfaces and exospheres are continuously interacting with radiation, charged particles, and internal energy sources. Mercury provides a template, demonstrating that what appears static from afar may, under sufficient resolution, be dynamic and persistent. The challenge is that these changes are cumulative, not instantaneous. Small deviations from predicted equilibrium accumulate over centuries and millennia, producing measurable shifts without dramatic events. Photon-stimulated desorption, solar wind interactions, thermal cycling, and magnetic asymmetry operate quietly, atom by atom, particle by particle. Hollows evolve, volatiles migrate, thermal anomalies persist. From a distance, these processes are invisible, but once measured with precision, the planet reveals itself as active, restless, and far from equilibrium. This also reframes the role of measurement itself. Reality is independent of observation. Mercury does not act differently when observed, but your understanding of its activity depends entirely on the sensitivity and resolution of instruments. Where earlier instruments failed to resolve subtle thermal gradients or directional chemical flows, Webb reveals them clearly. Observation does not create activity, it exposes it. The unease comes not from mystery, but from precision, from the realization that the universe is far more complex than assumptions based on limited data can capture. The implication is unsettling because it extends beyond Mercury. If small, slow, and persistent processes dominate at the boundary conditions represented by Mercury, then similar phenomena may operate across the solar system and potentially across the galaxy. Planetary surfaces may continually evolve at atomic, chemical, and thermal scales. Equilibrium may be provisional. Stability may be a perception imposed by observational limits. In this context, Mercury is both a singular laboratory and a harbinger of hidden complexity elsewhere. You are left with a universe that is persistent, patient, and quietly active. Systems may appear stable, static, or complete, yet they may be continually transformed by subtle forces that only become visible under close scrutiny. Mercury demonstrates that activity is not always obvious. It is continuous, directional, and cumulative. Processes that seem negligible in human terms dominate over longer scales, quietly reshaping worlds. The question that remains is not an idle one. It is an invitation to reconsider assumptions about time, scale, and process. If a small, sun-scorched planet like Mercury behaves this way, what other objects, regions, or systems have quietly persisted in their own restless evolution, hidden from view until the instruments are sensitive enough to reveal them? Each measurement you make narrows uncertainty, yet simultaneously expands the horizon of implication. Mercury is a warning. Reality is patient, subtle, and often stranger than first observation suggests. You are confronted with an uncomfortable realization. The universe may be continuously active in ways that are imperceptible until measured. Worlds you considered inert may be quietly transforming, never fully at rest, and only appearing strange when observed with sufficient clarity. Mercury is not unique in its persistence. It is a mirror, reflecting the possibility that much of reality behaves in ways you have not yet noticed, and that every precise observation reveals a deeper, ongoing, and quietly unsettling dynamism.